Hello, I am Eric Chacón. I'm going to present my approach for supervising student research projects. First, when I supervise a student, I aim for them to have a good understanding of the methods and applications they do. This is important for them to be able to extrapolate this knowledge in new projects and in their future career. I promote critical thinking. I think this is important to questions about the adequacy of the methods, if some assumptions are held, if the interpretation we are using is adequate, and to be able to identify if new methods are required, if new extensions are required. I encourage collaboration, and in particular, I collaborate with them. I get involved with the project, and I try for them to collaborate also with some colleagues from other disciplines. An important aspect is for them to have independence at the end of the project. I think this is important for them to be able to, in the future, to define their own problem, define their own way to analyze, and actually to be useful not only in academia but also in industry. And finally, to also support their career development, in the sense that we can adapt the project we are working on depending on what is their future interest. On the other hand, as usual, we have regular meetings. We structure very well the project through milestones, but more importantly, I want them to have very good practices for reproducibility and collaboration. I think this is important for being able to share this project, for being able to go back to the project and make extensions and so on, even for other people to use it. So I introduce them to version controls, open source tools, and also some documentation standards. I am very active when we work together. I get involved with the methods, with the software, and so on, and it's a way for me to show them how they could do things as an example. And finally, I encourage them to disseminate their work at seminars, conferences, and submit to journals. With respect to my project, the first one is about nowcasting disease incidents with machine learning algorithms. When we talk about nowcast incidents, it happens because in disease incidents, sometimes the reported cases are actually not updated adequately, and the actual number of cases is much bigger than the reported cases. So the idea here is how we can predict the actual number of cases using this underreported number of cases. So we can take to the historical data, the historical behavior, and model these two mechanisms, the actual evolution of the disease, but also the evolution of the reporting probability. We have seen previously that this reporting probability we can model parametrically, okay, so we can adapt this now using, for example, some machine learning algorithms. In this case, we're modeling the expected number of cases on time t reported with delay d, this is the expected, with respect to the true intensity and the probability of reporting the cases. This has some parameters, alpha, that has to be estimated, but then this true intensity can also be modeled with more complex algorithms rather than a linear predictor, and that we have some parameters beta. So the idea here is to estimate both parameters immediately, and we could again use more sophisticated machine learning algorithms for this nowcasting application. On the other hand, I have a project also for spatial data integration. In this case, we have this scenario where data is observed at different sampling units. Here you can see this data set is at low resolution, high resolution, and we could even have data that are observed at aggregated irregular areas. So how we can handle this? We have an approach where we have latent processes for each response variable and for each predictor, and then we associated it with the aggregated predictors and the aggregated responses, and then we associate them with the data. Okay, we have seen that these work very well, but then the way that we define each of these latent Gaussian or latent process, it can be different. For example, if we define them as a Gaussian process, we know that there is this connection of a Gaussian process defined of a point and a Gaussian process defined of a region. And we could use other machine learning algorithm with adequate cross-validation for spatial data, for example. No? So the idea here is explore other machine learning algorithms to tackle this problem of chain of support.